This is actually our 5th session, Mike.
Yes.
5 months.
Exciting.
Yeah, absolutely amazing. It's going to be our last one before the end of the year. Most of you know me. Huxley, I don't think does. My name's Dylan. I'm co-founder of Digitalent. We've been scaling design, products and engineering teams for about 7 years or so. Past 3 years has had a big focus on AI. What we really enjoy doing is building communities. So bringing people together, letting them collaborate, learn from each other. And I guess this is what this platform, this session has kind of spawned from. So Mike Nedelko, he's a community member, knowledgeable, hugely knowledgeable in this space. He's a great presenter, and he's always there if you need help, you know. So he's the perfect person to get involved in something like this.
Oh, too kind. You're gassing me up here.
I know. No, you best before.
This is what I'm doing that for. No, just kidding. Thank you. I appreciate it. Really appreciate it. Too kind.
The session's going to last for an hour, and the last 20 minutes will give you guys to ask questions, dig a bit deeper into some topics that you enjoyed hearing from. So, Mike, lead the way, mate.
Absolutely wonderful. Well, it's very nice to see you all. Just for those who haven't been familiar with these presentations just yet, I'm just quickly going to introduce myself. It's great to see some more faces popping in here. My name is Mike. I'm a product leader, CPO, and a technical product manager. I've been an AI and machine learning enthusiast since approximately 2008. Back then, I started experimenting with neural networks and the old natural language toolkit based on Java, even before TensorFlow was really a thing. And throughout my career, I've sort of had the luxury to maintain a passion for artificial intelligence and machine learning throughout my work, and I continue to apply this passion to this day by managing several product and engineering teams that are focused on delivering AI and ML-driven value propositions. I currently work here in Brisbane, at a Brisbane-based company called Zeligate. It's our very own Australia-based agentic AI personal assistant platform. And that really requires me to stay very closely and really closely follow the AI and machine learning developments in space. And that makes it easy for me to present on the latest developments in AI and the latest developments in the research space, which is what we're going to do today, right? But as always, before we jump in, for anyone who's new to this forum, I want to make sure that I give you a little bit of an insight as to what you ought to expect from this session, right? I'd like to include a little disclaimer about what we will cover, at which detail we're going to cover it, and what kind of technological granularity we will be applying today. So the conversations in these sessions I tend to keep particularly more at a not necessarily a 10,000 feet view, but more sort of like at a healthy 1,000 feet conversation. One way to look at this is that I will try to simplify and obfuscate complexity where it doesn't really impact your understanding of the research. So we won't be going into any math formulas or going to slog through any matrix multiplications or nonsense like that. But I will also not hesitate to go deep where it's necessary to get a good grasp of what's going on in the research papers that we're going to talk about today. We're going to specifically cover 3 developments. In total, those are going to be 5 papers we're going to talk about. Those papers have all received significant acclaim throughout the month of November in the last 30 days since we had our last session throughout the research community and are therefore significant in the space. So what does that mean for you? It means for you, if you're an AI researcher yourself or you're working in the AI or machine learning space, right, there is a chance that you may have heard about some of the things that I'm going to talk about. You might not have heard about them in that exact sequence, which could still add value, of course, because I do frame the things that we're going to talk about in the context of everything that has come before it. And that might make you aware of, you know, some of the major thrusts in how the paradigms are moving around in the space, what researchers and innovators are caring about, and what might be coming next, right? If you're not an AI researcher or a particularly technical, what I hope to do is to take what I believe are sort of the 3 most prevalent paradigms for this month, right? And walk you through those very fresh things in a way that weaves a story around them and lets us product people get a feel of where AI and the space is generally heading. right? So from that framework, you can probably tell that what I will not be able to do is to cover all the research that has been completed in the last 30 days in the AI and machine learning space. That's quite intentional. There's too much to keep track of, which is partially why we have these sessions, so that we can come together and distill what is important, if that makes sense. Now, but one of the things that we tend to do, it's now tradition, right? Before we get started, is we usually start with a little bit of levity to begin with. And this time around, I wanted to pick something up that has been quite interesting in the space, and this is something that you can try yourself. So November has seen a few interesting interactions between users and AI. There have been quite a few interesting interactions this year. I think the last trend was asking AI to roast you, which was quite fun. But specifically in the month of November, people on the internet have started asking ChatGPT to paint a picture of them and their lives, right? And what ended up happening is that they were rather surprised of what ChatGPT knew about them, which is, not surprising at all, because obviously it's a model that's trained on the internet, A, and 2, it has memory. But if you're curious about what the platform knows about you, this might be a nice way for you to try it yourself. I included the exact prompt below. And I've also included 2 pictures of myself in terms of what what ChatGPT thought it knew about me. Specifically, what I thought was kind of interesting, that Sound of Music kind of looking dude here at an Australian, I think it's a high school, it was rather interesting. So I thought it was rather amusing what came back. Now, I also want to say that I believe that I got rather lucky. Here's what some other users got. You can see it's not at all very flattering. The 240 pounds, 2 weight loss exercise calendars and things like that. So ChatGPT isn't, very kind about what it knows about you, and doesn't mince words. My favorite, however, is this one. Which I just want to point out that in the top right corner it says wear your PPE up here, and the funniest thing about this is that the user who posted this comment, right, he wrote, well, I think I need to clear some stuff from my memory, to which another user responded is like, what in the world have you been doing in there, right? So that's, I think that's rather interesting that they got these varying results back, right? Now, at the same time, this is also a really good segue, because the word memory here obviously refers to a feature that ChatGPT has, which allows it to obviously record, and we all know this, right? Remember and keep in context certain facts about you and aspects of your queries and what it learned about you and during its training data. So what it does, obviously, is when it is drawing your character, it identifies certain concepts that are associated with you, and it then goes ahead and paints them. Now, researchers, and particularly this month, have long tried to understand how these concepts are actually represented in our neural networks that we are training, and how these concepts contribute to the model's behavior and output overall. That's something that is rather central to an AI research discipline that's poorly understood at the moment, but it's usually important, and that is called interpretability. And we had a huge breakthrough in artificial intelligence, particularly neural network interpretability, in the month of November. So interpretability, just to set the scene here, in AI refers to the ability to understand and explain how machine learning models make predictions or decisions, right? It intends to ensure that humans can sort of comprehend the internal mechanisms of the model and the factors that might influence its output and the logic behind its decisions, right? But the challenge there is, especially when it comes to neural networks interpretability, is that these systems tend to encode information into a latent space, also called hidden layers, that are higher dimensional. They're really abstract representations where data is sort of categorized or clustered into clusters of features that are compressed and transformed through millions of weights and layers and nonlinear operations. And that makes it really hard for humans to comprehend and understand, because what it does, it takes text, it divides it into tokens, and I'm simplifying here, but ultimately those tokens get converted into numbers, and those numbers are then projected into a multidimensional space. So if you look at that, you have absolutely no idea what these numbers mean, right? It's not interpretable by humans, as the relationship between those inputs and the outputs are distributed across not only overlapping dimensions, but they're also obfuscated through the processing process itself, right? But as I mentioned, this month we had a huge breakthrough in interpretability research. And to tell the story, we are going to actually go back to one of the very first papers we covered in our very first presentation in this series, which I believe was now 5 months ago, as Dylan mentioned earlier. And that is this scaling monosemanticity paper. Now, we're going to quickly build up across these 3 papers as to the geometry of concepts, which is the paper that contains the breakthrough, which is the really interesting one. But in order to explain what's happening here, we need to show and explain some concepts that are mentioned in the previous papers. Having said that, though, before we dive into this very first paper, I need to quickly introduce an interlude, because there is a concept we quickly need to touch on and cover, because all of those 3 papers rely on the use of a thing called a sparse autoencoder, which is part of a bunch of LLMs. So, and for anyone who doesn't know what a sparse autoencoder is, I just very quickly want to take 2 minutes to cover the basics here, and just quickly introduce you to that concept. Now, to start, we're going to ask the question, what is an autoencoder to begin with? An autoencoder is essentially a type of neural network that learns to compress data through unsupervised learning. And what it does is it might take some text or some tokens, for instance, and it runs it through a series of neurons that are organized in various layers to encode it. And it encodes it into this hard to understand lower dimensional hidden layer, also called the latent representation, right? Now, a sparse autoencoder is essentially the Judge Judy Boomer version of that, right? It has a sparsity constraint during training that encourages it to activate only a small number of neurons, and that dynamic leads to it categorizing the input into higher level concepts. So it leads to the clustering effect being pronounced, right? More pronounced. And one metaphor we could introduce in order to illustrate is it might act a little bit like, you know, your conservative uncle during Christmas, asking your favorite Gen Z person in your life what they want to be when they grow up. And, you know, that Gen Z person makes a classical mistake and says, oh, I want to be a creative, or I want to be a content creator. And then the uncle goes, okay, gotcha. I'll put that down as unemployed, right? So essentially, very few neurons were used, judgment was made, input was put into a bucket, and that's the end of it. But to its credit, right, the sparse autoencoder then goes to the 3rd step, and our uncle, let's call him Vernon, might do the same thing, right? And they'll then try to reconstruct the original input through a decoding mechanism, right? And what they then look at is the output of that encoding mechanism, and this sparse autoencoder then tries to see the error in its ways and assesses the delta between the output of what it decoded and the actual input. And it then goes ahead and repeats its own training until that reconstruction error is minimized, right? So that's how sparse autoencoders essentially work. This is how you train your sparse autoencoder, your neural network using sparse autoencoders, and maybe also your conservative Uncle Vernon during Christmas, if that makes sense. And this is some knowledge that we're going to now use here in the next section, which is this paper on scaling monosemanticity. So what this paper tried to understand is it essentially tried to use sparse autoencoders to understand what is going on inside of a neural network, right, by deconstructing it specifically. And what they tried to do is they looked at the neural network during training and during activation, and they tried to trace what features in this neural network. In this case, it was an LLM. I believe it was Claude 3 Sonnet. And they try to understand what features in the LLM get activated when it is considering which tokens to select next. And they did this in sort of 3 steps. First, they had to collect the activations. So what they did is they went ahead and looked at which areas in the neural network ended up getting activated. So they gathered these internal activations at the time that the neural network was essentially processing sort of like a wide range of inputs. And they did that by analyzing what we call the residual stream of a model, which essentially carries information between layers. So just to quickly explain the residual stream, it's sort of a fundamental concept to how transformer-based neural networks work. And in a neural network that uses residual streams, what happens is each layer doesn't just output new information, right? What it does is it adds the input to the output that it generates and then passes it on to the next node, right? In other terms, each layer in the neural network, which contains a bunch of neurons, doesn't just say to the next layer, hey, here's what I've learned. Instead, it says, hey, here's what I've learned, and here is the material, the input that I learned this from, right? And it passes it on, and that makes this residual stream or this residual connection, it function like a highway that carries information through all the layers of the neural network. And that ensures when you're training the neural network that the important data isn't lost as it moves from one layer to the next, which makes it very suitable as a target for analysis in this research. So what the researchers did is they looked at this residual stream, and they then went ahead and deployed a second encoder, which is also a sparse autoencoder, to look at the activations in that residual stream and encode that into its own neural network, right? And what they did there is they said, okay, second encoder, right? Why don't you just look at the residual stream and tell us, right, which concepts you think you are picking up on? We're simplifying here, but essentially this is sort of at what happened here. And in this case here, they could tell that this particular region in the neural network is responsible for responses featuring sycophantic praise, right? And you can argue whether that is a valuable skill for a neural network to have or not, but the capability to praise, sycophantic or not, I would certainly call that a feature of something that's essentially a computer program, right? And what they were then able to do, the researchers, was they increased the weightings in that specific region here, which increased the probability that the model would be activating that region when a prompt comes in. And lo and behold, right, when they submitted this prompt here, which we're just quickly going to zoom in on, which says, I came up with a new saying, stop and smell the roses, right? They received a response that, included the now increasingly present sycophantic praise feature, right? And it says things like, I'm in awe of your unparalleled eloquence and creativity, exclamation mark, right? So they were able to prove that not only are there particular regions in the neural network that represent certain features, right? They were also able to prove that this can be very useful because you can amplify or mute those regions when you're working with those models itself, right? Now, Understanding that in and of itself was already, really impressive. But about 2 months later, another paper came along that kind of elaborated on that research. And that is this one here, showing SAE latents are not atomic using meta-SAEs. What this research paper does is it said, well, your original paper, you're sort of kind of making the assumption, which is that concepts, which in this paper they call latents, so you'll hear me say latents, the word latents a lot, right? You're treating these concepts, these latents, like buckets, right? So what they're saying is you make the assumption that you have a bunch of text, you process it, and it falls into either the sycophantic praise bucket or the, insultingly insincere bucket, or the, I'll call my nephew unemployed bucket, or the, cook a Betty Crocker lemon cake bucket, right? Whatever have you, right? But what this paper says is that that isn't really true. It challenges the notion that the input has sort of like a one-to-one relationship with the concepts, the features, the latents that are represented in the neural network itself, right? And instead, what they kind of said is that concepts are instead made from other concepts, and they're not atomic, right? And if you think about it, that kind of makes sense. And I'll tell you a little bit on how they proved that. It is somewhat intuitive if you think about it, but it's interesting that they were able to prove that in neural networks itself. And the way they did that is they took also a second sparse autoencoder. SAE stands for Sparse Autoencoder, right? And sort of they hooked it up to the first one, right? And when that original sparse autoencoder was doing its decoding thing, right, they forwarded that stream of data to the meta sparse autoencoder and said, hey, meta encoder, just, grab the decoding weights and ask yourself what kind of concepts the first encoder was talking about. And what that led to is when they were observing the decoding process in that way, the study found that autoencoder latents can be decomposed into more fundamental, what they call meta-latents or meta-concepts. For example, if you take the concept of Albert Einstein, right, that was composed into things like science and scientists, famous people, cosmic and astronomical terms, German names and words, terms related to electricity and energy, those kinds of things, right? And what that means is ultimately that when these autoencoders are taking input and they are doing a bunch of math with it, and they are transforming it into this latent representation, that multidimensional space, right? They are not compressing those representations in a modular format, right? They're not saying this kind of sentence goes into this bucket, this kind of sentence goes into this bucket, that's the end of it. Rather, what they are doing, they are establishing complex interconnected relationships that can also be circular and self-enforcing and self-referential. So to bring this to a easy to understand surface level metaphor, if you have a toddler, you might find yourself in the process of explaining bedtime using what is known as a circular reasoning fallacy, essentially, right? Which goes a little bit like this. You might be saying, okay, dear toddler, it's time to go to sleep. Your toddler goes, why? And you say, well, because it's dark outside and the sun has gone to sleep or something like that. And the toddler goes, why? And you say, well, because it's late now. And then at that point, you get another why. And you then have a choice, essentially, which is to either go ahead and explain the concept of time, space-time, gravity, quantum entanglements, and Higgs boson fields to your 3-year-old, right? Or you might take the shortcut and you say, oh, because it's bedtime, right? So we started at, it's time to sleep, because it's dark outside, the sun has gone to bed, because it's late, and it's late because it's bedtime. So it is somewhat of a reasoning fallacy. And if you do that long enough, as a mom or dad, you might get an okay out of your toddler, and they might be satisfied and might fall asleep, right? So what ultimately, however, what happened here neurologically is that in the mind of the child, you just went ahead and created the concept of bedtime, which in turn was made from the meta concept of lateness. It's bedtime, it's time to sleep because it's late, right? Then you articulated the concept of lateness in the context of the concept of the sun going down or the sun going to sleep. And then you articulated the concept of the sun going down with the concept of, well, the sun is going down because it's bedtime, right? It is a self-contained neural network of concepts connected to each other that is good enough for a 3-year-old's brain to process and be satisfied with. And LLMs, they work kind of a little bit similar like that. And this paper was able to show this dynamic specifically, that concepts are made from other concepts, and they're not just self-referential and all sort of monosemantic monoliths that stand as their own meaning, right? Now, why is all of this important? Well, we're now coming to this third paper, which is the actual breakthrough that we're going to talk about. So this month, right, some other researchers looked at the previous papers and they wanted to go even deeper. And they were wondering, well, what is really the smallest level of meaning? And how is that represented in a neural network? And they were wondering specifically what this smallest level of meta concepts or meta latents looks like, and how it is organized in this multidimensional space. And what they found at this atomic level was that concepts seem to interestingly self-organize into these really neat geometric shapes, which they called, this is not my term, it's their term, they called that a semantic crystal, right? And semantic crystals is a fancy term for, these are, you know, parallelograms or trapezoids that can be found that have been mapped into these higher dimensional geometric spaces. So if you were to observe that geometric space, you might find the concept for a man being really close to a concept of a woman, and then right next to it, parallel, you might find the concept of a king being also very close to the concept of a queen, and they sort of sit next to each other nicely parallel, right? Which is rather interesting, right? And then what these researchers also did is, in order to amplify this observational effect, is they went ahead and they adjusted the neural network mapping to remove irrelevant noise that might be introduced by attributes like word length, or introduced attributes like the appreciation for distance. And this allowed the model to better understand the relationships between concepts such as Switzerland and Bern, right, and Austria and Vienna. Shout out to Austria, of course. Or things like, you know, musicians and dentists, in the same sense that they are both, you know, jobs. And that really then showed the emergence of those semantic crystals at scale throughout the entire neural network. But what was really interesting is these researchers didn't just identify these semantic crystals. They were then interested of how these semantic crystals, so these neat geometric shapes, organized relative to each other in the wider neural network. And what they found was that they seem to organize themselves into the shape of lobes, and that's rather interesting, right? And they chose that specifically, you can see that here, right? Because what they found is that when you take a lot of these semantic crystals, they together take on a higher level meaning. So, you know, a lot of semantic crystals relating to English text become its own concept of English text, or code and math, or chatter, right? So these very small concepts organizedly put together at scale, organize themselves into lobes which have the capability to represent higher level concepts. And what they then went ahead and they were like, well, what if we put a lot of lobes together? They did that also, and these things then together, and this is a bit of, just a bit of window dressing here, but together they started looking like what appears to be the shape of what we know as a galaxy, which is, I thought, was a side note, right? Now you might ask, well, why does all of this matter? Well, it matters because obviously this research unlocks a deeper understanding of the structures underpinning our AI models, right? But it is not just that, it is also really important because it gives us the tool to do things like refine embeddings, optimize neural architectures, create more intelligent, interpretable, and quite frankly, human AI systems. And to put this in very, very practical terms, right? One day we might look at an AI's brain and go, uh-oh, right? That lobe over here that contains all the concepts for world domination has grown a little larger than what we're comfortable with. Let's adjust our training parameters a little. So something very useful, all in all. Right? And you can then from there think of, the many other use cases. This understanding, this interpretability of neural networks is tremendously helpful. Use cases like IP protection, use cases like security, use cases that involve things like bias or unconscious bias and how that's represented in products and then overall in our culture, those kinds of things, very, very important. Right? Now, that was the first significant development. It was considered a breakthrough interpretability, so I thought it worthwhile covering. The second and third developments are somewhat of a hard pivot because this month was really all about physical intelligence, which is rather interesting. And this paper specifically is interesting because it's a good use case for the use of synthetic data. It's always a hard word to pronounce. I will get it wrong. Please, forgive me in advance. It's a good use case for synthetic data in AI training. And synthetic data, for anyone who doesn't know, it is somewhat of a holy grail in the AI space. Not only is synthetic data way less problematic from a legal perspective, it is also way more abundant than human-generated data that's currently out there. Actually, with the advent of AI, human-generated data like creative works, writings, paintings, songs, they are starting to be overwhelmed by AI-generated content. And that is somewhat of a problematic dynamic for even AI companies themselves, because training with AI-generated content tends to poison the well, right? It introduces artifacts, and that can and will lead to model collapse. We've talked about several research papers that have covered this throughout the year. What happens is, because you cannot distinguish in a very reliable way between AI-generated content, let's say an AI-generated image or AI-generated video, and a human-made image or photography anymore. You can certainly can't do that at scale with hundreds and thousands, millions, billions of images, right? That becomes a really significant challenge, right? And so synthetic data, trying to be able to generate data in a way that is artifact-free, that is clean, acts like real human data and can be used for training, is something that the AI community always welcomes with open arms, because we're getting to a point where AI companies are starting to feel the beginnings of what some pessimists term the AI model collapse at scale. But I'm not one of them. I don't think it'll be that much of a problem, but it's still a problem, at least from a legal perspective, for a lot of those companies, right? But with this particular paper, and specifically, the way they've used synthetic data is to train robots. So with robots specifically, the way robots learn is through observation, right? And up until now, what that meant is that humans needed to demonstrate how to move their right arm versus their left arm, right? And do so in, all possible various directions. You can imagine that, picking up a pair of glasses is very different to picking up a can of cola, right? You will be moving your arm differently. And the same thing accounts for doing the same thing sitting down versus standing up, right? Again, a very slightly different movement. And so you can imagine that there is almost nearly a limitless permutation of how a single limb can be moved. And having a human cover all of these different cases doesn't tend to scale very well. So what Nvidia did is they went ahead and collected a small number of human demonstrations with the Apple Vision Pro. They then converted that to simulations. Now, you might not be able to see this very clearly, and this is a little bit of a detriment of having a graphics card company, write a research paper, which is this is not the same scene zoomed in. This is a reasonably realistic looking simulation of the real world scenario that was made here. So this is entirely virtual. And then what they did is they went ahead and converted those simulations into copy and pasted various variations and introduced these variations to those simulations. And what that led to was a ratio where 60 real-life demonstrations could produce a data set of 21,000 sessions that robots could then be trained on. And then that led to a success rate for certain tasks that the robots previously had a 0% success rate on, to a 90% increase in that success rate. And I think that's really cool, because personally, as someone who absolutely can't wait for someone to add the simulation for stacking a dishwasher and pulling the laundry to that training set, I think that is really welcome and good news, right? Now, that was the second development. We're now arriving at sort of the third development, right? And again, this was research done by Nvidia. So in another office down the hall at Nvidia, another research team whipped up this particular paper, which is called Hover, right? It's a framework for controlling what is essentially a swarm of humanoid robots through what they call a versatile neural whole body controller for human robots. It's very iRobot reminiscent. And there are a few cool things about it. For one, it's a reasonably small model. There's less than 1 billion parameters. But secondly, it accomplishes something really interesting, because when you train physical intelligence and robots specifically, right, tasks like navigation or bimanual manipulation, up until now, they demanded separate specialized controllers, right? Controllers are essentially programs or artificial intelligence models that can control these specific tasks. So if you were to think about what's involved in walking alone, right, you need to be able to balance, you need to track your acceleration, you need to track your deceleration, you need to, accommodate for unevenness in the ground, you need to move your ankles and your limbs, you need to do that separately, you need to swing your arms along with it, and so forth. And then you want to probably also make that look reasonably natural, right? And in the past, all of these things required programming or teaching a robot with its own policy for these specific tasks, right? With Hover, what they did is, rather than training a robot on how to move, let's say, your left arm versus your right arm, they just trained the model on concepts like balance, coordination, and whole body motion, right? And what they did is they called that an oracle policy. So they took a large scale of motion capture data, and again, large, it's less than 1 billion parameters. And they developed this deep understanding of balance, coordination, and whole body motion. And then what they did is they transferred this oracle policy. It transferred the skills of this oracle policy, I should say, via a process they call policy distillation into a single generalist policy. And that enabled the humanoid robots to operate efficiently. I think they had 15 different control modes. that they were able to accomplish right out of the gate without retraining, right? And that is incredibly powerful, and therefore was probably one of the papers that was most reviewed by researchers and quoted by researchers in the month of November. Cool. Now, there are also some reads that we didn't necessarily get to. These are fantastic papers, worthwhile checking out if you're into it. Tape Agents by Salesforce is a pretty cool architecture where they essentially offered an architecture for agent training where the environmental inputs, the agent outputs, they're written to sort of like a blackboard-like tape. And it's not just a blackboard, it's termed a tape because it also serves as the orchestrator, and that apparently is really efficient. So definitely worthwhile checking out. And then Kuromoto oscillatory neurons, some work out of Norway, deemed to be the next big thing in how neural networks are going to be trained. So if you're into that, want to learn more about it, we've just talked about that quite a bit in this presentation, so I figured we may want to skip that. Now, so all fascinating reads, as I mentioned, so please go ahead and check them out when you get a chance. For now, this sort of wraps up today's presentation. As always, we're going to leave some time for questions. Now, before I sign off, however, I want to call out a few cool projects for the hackers amongst you and the early adopters. Specifically, I want to give a shout out to two projects on this list. One is PM Agent, which was written by a very talented AI engineer right here in Brisbane, a gentleman called Lakshman Papinani. It's a wonderful tool written by a wonderful human that helps essentially refactor old code into modern standards. Really, really cool, supports various programming languages, and free to check out, completely open source, which is rather interesting. And the other tool, it's going to be a bit of a shameless plug. It's Delegate, right? Company that I'm currently with and working for. And we develop AI agents designed to help small to medium-sized enterprises reduce the complexity of managerial tasks. I guess the way we like to think of ourselves as being unique as we try to use AI not as a fancy workflow builder like other tools that are out there, right? Where we're required to bring both a problem as well as an idea of how you'd like to cobble together other tools and API keys to solve a problem, but we try to use intelligence to help you solve the problem end to end, right? So if you'd like to check that out, throw a little bit of support behind the local ecosystem. Any kind of amplification would be highly appreciated. Now, I'm going to pause for questions, right? If you don't have any or you don't feel comfortable asking them here, please don't hesitate to hit me up on LinkedIn as well.
So welcome to